Hello, and welcome to the video accompaniment for Chapter 8, Section 1 of our text. This whole chapter is about counting. We call this Introduction to Counting. And the first section starts off with the multiplication and addition principles. So after reading through the section, working through some problems, and watching this video, you should be able to see a problem, be able to create a procedure to solve that problem, reduce that to procedure to tasks, and then determine how many possible procedures are possible. So it's sort of a step-by-step guide for counting the number of ways to solve a problem. This is something called enumerative combinatorics, which is essentially counting. But we need to develop some procedures and set some ground rules for counting, hence these principles. So in particular, sometimes you'll want to multiply the number of options together. It's called the multiplication principle. And sometimes you'll want to add the number of possibilities together. This is the addition principle. And so the multiplication principle and addition principle state when it's okay to do this, when one should multiply, when one should add the number of ways to do a procedure. And therefore to solve a problem or solve some sort of configuration problem, to figure out how many ways there are to configure something, because that's really what combinatorics is. It's configurations of objects. Enumerative combinatorics then would be counting the number of objects. And that's what we're starting on today. Let's get started. So let's just first take a look at an example. The problem in this example is we need to pick out a set of shoes and a set of socks. So we have 3 different kinds of shoes and 4 different kinds of socks, and we want to know, well, how many ways are there to pick out a pair of shoes and socks together? Okay, so how should we proceed with this? Likely you may already know the answer should be 12, the multiplication between them. And why is this? Well, in some way, let me just sort of set up the statement of the multiplication principle. I'm going to use some notation here. So we have 3 different kinds of shoes, 4 different kinds of socks. So my procedure here, so a solution to the problem is a pair of shoes together with a pair of socks, right? That would solve the problem if I could pick that out, and I want to know how many ways are there to solve the problem. So for that, I'll generate this procedure. And the procedure in this case, it could be I see two ways of doing this. I'll call this T1 for task 1. Or sorry, wait, let me state the procedure. What is the procedure here? Well, let's say we want to, 1, we're going to pick the shoes. We'll just pick some ordering. Pick shoes, and 2, pick socks. And we could have done this the other way around. The answer is not going to matter in this case. More on that later. Procedure, and so what I want to do then pick socks, right? So what I want to do is reduce this to a list of tasks. So how am I going to do this? Tasks. So task 1 would be to pick the shoes out. Remember, there are how many ways of doing this? 4. Now how many shoes do we have? We have 3 different kinds of shoes. So this would mean my task 1, how many ways are there to do task 1? 3 ways. And then for task 2, how many ways are there to do that? So task 2 would be picking the socks. And there are 4 ways to do that. And so it's pretty self-evident that the number of ways to complete the entire procedure to do T1 and then T2 would be to multiply 3 and 4. One way we can see this is in a tree diagram. So here's where I'm starting, and then I'll perform task 1. Well, actually, let's set the stage a little bit better. Let's say X, Y, and Z are the shoe choices. So maybe X is sandals and Y is high heels and Z are sneakers, something like that. That could be it, but I'll just use X, Y, and Z to keep it general. And then picking the socks. I don't know, we have 4 different kinds of socks. Let's call them A, B, C, and D. So pick your favorite 4 different kinds of socks, maybe polka dots or stripes. And so doing this procedure means first picking the shoes. So the outcome, here I'm going to list the outcome of the first task. We could have picked X, Y, or Z. And so that's task 1 is picking this, and this is that outcome. Either X, Y, or Z must have happened. And then off of each one of those, I'm going to pick the socks. So this is really just a rather nice way to sort of diagram all the different solutions to this. And so I could pick A, B, and C or D after picking X. I could pick A, B, C, or D after picking Y. And same with after picking Z, I could pick those. And so what are all the different possibilities? Well, it's all these end vertices. It's all the leaves of this tree diagram. And it's pretty easy to see now that the answer should be 12 since we had 3 first choices and 4 branches coming off of each one of those. And so 12 total. All right, so this example is meant to motivate the multiplication principle. How does this work in general? Let's say a procedure consists of an arbitrary number of tasks, like m tasks for some m, and there's a certain number of ways of doing each thing. Then essentially what the multiplication principle is saying is we just need to multiply those all together. So here's the statement of the multiplication principle. If we want to count the number of ways to perform a procedure, that's also some problem, then we'll reduce that procedure to a number of tasks. So like I said, m tasks here, ti, for each I. And how many ways are there to perform each task? So how many ways are there to do ti? There are n sub I ways of performing ti. And then the total number of ways of performing the procedure then would be just the product of all of them. Multiply all the number of ways together. All right, so let's see this in action. Let's say we have a license plate and it consists of 3 letters followed by 4 numbers. And we want to know, well, how many different license plates can one make with different license plates that one can make using 3 letters followed by 4 numbers. And so for things like this, this is really representing a string where the first 3 entries of the string are letters and the last 4 entries of the string are numbers. So we have something that looks like this: 1, 2, 3, 1, 2, 3, 4. So for each one of these, I can put a letter, A through Z, A through Z, A through Z, and then in each one of these, I'll put a digit, a number 1 through 9. Sorry, I could also be 0, right? 0 through 9, 0 through 9, 0 through 9, 0 through 9. And so in this case, a procedure to solve this problem, to know how many ways there are to fill up this license plate, my procedure might be pick the first letter. So that would be step 1. Step 2 would be pick the second letter, and so on. And then it would be step 4 would be to pick a letter, and we would continue that on all the way to step 7 would be our last step, and that would also be to pick a number. Sorry, I should have said number before. Let me erase that. Pick a number. And so we have these 7 tasks. Well, how many ways are there to do each task? Well, the first 3 of them, I pick a letter. How many letters are there? Let's assume we're using the English alphabet. There are 26 ways each. And then how many ways are there to pick a digit? So to pick a number for those 4 slots, well, there's 10 ways to do that, 0 through 9, 10 ways each. And so I could, I like to write it out like this. There's 26 ways, 26 ways, 26 ways, 10 ways, 10 ways, 10 ways, 10 ways. So if I list the number of ways up here, then the total number of ways to pick the procedure by the multiplication principle that we just saw is we multiply all of these together. So this would be 26 to the 3rd times 10 to the 4th. So a rather large number of ways to do this. Let's actually calculate it. Why not? Times 10 to the 4th. So about 175 million. Let's write it out. 175,760,000. And that's it. So that's how many ways to do this. And so that's the multiplication principle. Notice that what's happening here, right, it's one by one task. We do this thing and then we do this thing. There's no overlap. They can't be completed at the same time. You have to go in this order. And that's when we get to use the multiplication principle. So let's actually apply the multiplication principle to prove a result, and maybe that'll help us understand this multiplication principle a little bit better. So the theorem is that if we have two non-empty finite sets, and let's say cardinality of A is M and the cardinality of B is N, then the number of different functions from A to B is cardinality of B raised to the cardinality of A, or N to the M. Okay, so let's maybe start with my blobs. When I draw finite sets, we're dealing with two non-empty finite sets. And let's say this is A and this is B. And A's got some elements in it, and B's got some elements in it. So how can I build a function from A to B? Well, let's call these something. Let's call this A1, A2, up through. How many elements are in A? There are AM elements. And how many elements are in B? Let's call them B1, B2. There are n elements in B, so up through Bn. So how can I build a function? Well, remember, for a function, every element of A goes to exactly one element of B. Right? There can't be two arrows coming off of a single element, and every single element has to have at least one arrow coming off of it. And so that means, right, there's a collection of pairs. A1 has to be sent somewhere. A2 has to be sent somewhere, and so on, right? Each AM has to be sent to some location in B. And it's set to exactly one of them. And so for each one of these slots, how many choices do I have? Well, I have exactly many choices as there are elements in B. So that means there's n ways to do this, n ways to do this, n ways to do this. So I've reduced it to a procedure. Again, here my procedure would be assign an element of B to A1. Next one would be assign an element of B to A2. And remember, those can double up. So I have n options for both of those. I could hit the same element. That's fine. It just won't be one-to-one anymore. But we're just counting functions this time. And so this means total number of ways would be n times n times n. How many n's are there? Well, there's m total elements in A. And so that's how many tasks there are then. And so there should be m total of these, m times. And so that is n to the m, or we could write that as cardinality of B raised to the cardinality of A if we want. And so we could consider that a proof. It's really just applying the multiplication principle and reducing this problem to a set of tasks. All right, what about one-to-one functions? If we want the number of one-to-one functions, we have to be a little bit more careful. And our equation is a little bit different. The number of one-to-one functions, excuse me, with the same setup as last time, and this time we'll assume m is less than or equal to n. Remember, if m is strictly greater than n, then it's impossible. There's no ways to do it. Remember back to chapter 5. And so this is saying the number of one-to-one functions is this. So let's figure this one out. So we have the same sort of setup. I can describe any function as a set of ordered pairs. Right? I can say where A1 goes. Same setup as last time with the A1 through AM and B1 through BN. So A1, where does that go? Where does A2 go? Where does A3 go? And so on. And lastly, where does AM go? Well, A1, if we start with A1, so here's our sequence of tasks again. The first one, T1, would be choose X in B such that A1 X is in the function. So we'll pick a certain element of B, and then T2 would be pick the next element, pick the element for A2. So how is this any different? Well, we have to be careful when we pick the element for A2. Remember, we want this to be a one-to-one function. And so this pick the element for A2 that isn't X. That isn't the one we used for the first one. This will ensure that we don't double up on any, right? We don't want to hit the same element in B twice. And so I could do this in any order, but if I start, with task 1, we'll just keep doing this, and we can't use anything we've used before. So if I start with A1, there's n ways to do this, or sorry, m ways to do this. No, n ways. We're picking an element of B, right? Should make sure we're doing it right. There's n ways here. There's n ways here to pick that. Careful, are there n ways there? No, we can't use A1. So there's one less ways to do that, n minus 1. So this is the idea. They all have to come after each other, and they might depend on what's happened previously. So there's n minus 2 ways to do this one, since we can't use either of the ones before. And once we get to the end, how many ways are there to do this? Well, we started with n, that was A1. A2 was n minus 1. A3 was n minus 2. So AM would be m minus 1. So this would be n minus m minus 1. Which is the same thing as saying n minus m plus 1. So there's that many ways to do that. That would be my last, because I've already picked m minus 1. I've already used m minus 1, and so I only have n minus m plus 1 choices for that last one. All right, so what does this look like then? The total number of ways. By the multiplication principle, I multiply these all together. N times n minus 1 times n minus 2, all the way down to n minus m plus 1. And so we have this result here now. Great. But this is saying written a bit more compactly, and we'll run into this notation a lot in this chapter. And so I'd like to try and make it clear right now how this thing on the left is the same thing as the thing on the right. What I'll do is I'll multiply top and bottom. Why not? By how about n minus m factorial? I'll multiply on the top by n minus m factorial and then divide by n minus m factorial, so I haven't changed anything. And then look at what we would have on the top. We'd have n times n minus 1 times n minus 2 times n minus m plus 1 times n minus m factorial. So on top, it'll go all the way down to 1 times n minus 2, dot, 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 dot. I'll keep multiplying them together down to times 2 times 1. And then on the bottom, I have n minus m factorial. So on the top here, I expanded the n minus m factorial, right? That's n minus m times n minus m minus 1, and so on down to 2, down to 1. And so all of that together then gives me the n all the way down to 1. And that's the same thing as n factorial. So this is n factorial over n minus m factorial. It's just how factorials work out, right? All these n minus m factorial on the bottom cancels off with all the parts of the n factorial that are n minus m or less. And so that's why we just have n times n minus 1 down to n minus m plus 1. So since we know there's a multiplication and an addition principle, where does addition come into this? All we've seen so far is just multiplying a number of ways together. So how do we know when maybe we should add them? So we'll take a look at this example. How many 3-bit strings end in 1 or 0? So what are our 3-bit strings? Remember that each bit is either a 0 or a 1. And the 3 part of this, the 3-bit string, means there's 3 total bits. So we have a string that looks like 1, 2, 3, and each one is either a 0 or a 1. And so this question is asking something a little bit different than we've encountered. How many 3-bit strings end in 1 or 0? And so what we really need to do is we first need to count the number of strings that end in 1 and then count the number of strings that end in 0. And then it seems reasonable that we should add those together. So we actually we can think of this as maybe 2 procedures or just tasks and subtasks. So the first thing I'll do is I will choose a 3-bit string that ends in 1. And so this one, we already know there's a 1 in that spot. That leaves 2 options for this one and 2 options for that one, either a 0 or a 1. And so by the multiplication principle, there's four ways to pick this first one. And then here, well, this one ends in a 0. And again, we have 2 ways to do this, to pick a 0 or 1, and then 2 ways to pick a 0 or a 1 there. So again, we have 4 ways. And so now we ask ourselves, what should we do with these 2 4s? We're talking about doing one of these things or the other one. And so a solution to this looks like one of these guys, one of these ways to do it, or one of these ways to do it. Rather than pick one of these things and then pick one of these things, in which case we'd multiply them, we're deciding this or that. And so this is the addition principle. This is why we add them. So there's 8 total ways. Which is the same thing, right? If it ends in 1 or 0, that covers all the possibilities. We should get 2 to the 8 by the multiplication principle, so we can kind of verify that result. That makes sense. All right, what about another example? How many 3-bit strings end in 1 or begin with 0? Okay, similar setup. We can reduce this to tasks. So we'll pick that one, and then we'll pick this one. And so in this example, how many 3-bit strings end in 1? So this one is filled in, that's a 1, or begin with 0. So my other thing will be to pick the ones that begin with 0. So we already have that bit filled in. How many ways are there to do this? Well, we know we already decided that. So there's 2 ways here, 2 ways, 2 ways. So there's 4 ways to do this. Here, the 0. So we have 2 ways to do this, and 2 ways to do this. And so you might think, hey, this is just the same problem. We should add these together. But careful. In some sense, these tasks can be completed at the same time. So what I mean by that is over here, what are all my 4 options over here? Well, I could get, I'll list them out right here. I could do 1, 1, 1. I could do 1, 0, 1. I could do 0, 1, 1. I could do 0, 0, 1. Those are my 4 options, right? And over here, I also have my 4 options. I could do 0, 1, 1. I could do 0, 1, 0. I could do 0, 0, 1. I could do 0, 0, 0. So those are my total 8 options. But careful. Do you notice that this option is the same as that option? So that is, there's some overlap, and that's the only one. There's some overlap between these 2. And so how can I figure out the total number of ways? That's not the only overlap, is it? There's another one, 0, 1, 1. Did you catch that? I did it on purpose. So these 2 are shared among both of these. And so if I just added those together, well, that wouldn't work because we double counted. So how can I get rid of this double count? Well, I can toss one of the sets away. So if I throw this one out, and let's say I throw this one out from the count. So if I subtract 2 from this, 4 plus 4 minus 2 equals 6 total ways. So that's what I should really do, is I should throw out one copy of the duplicates, get them out of here, and then everything will be unique. So here we couldn't just add. The addition principle is going to say we add them when there's an option. But we have to be careful with the addition principle that the options can't be done at the same time, that there's no overlap between the options. Like in this one, we didn't have any overlap because it was impossible for a string to end with both 1 and end with 0. There was no overlap. Each set of solutions would be unique. Here, we had that issue. So let's see the statement of the addition principle, and be sure to look out for this sort of caveat to the addition principle, this overlap idea. So here's the statement of the addition principle. So again, we have a procedure consisting of forming a number of tasks, no 2 of which can be formed at the same time. Again, we'll label them T sub I, and there are N sub I ways to do each task. Now, the key part, I went over it really quickly, no 2 of which can be performed at the same time. That's what I was talking about in that last slide. This is saying, and there's no overlap between tasks. They can't be done simultaneously. And the addition principle is saying, so long as that's not the case, there's no overlap, and then we just add them all together. So what we're really doing here is we're counting unions of sets. What do I mean by that? Well, okay, so for each task T sub I, let A sub I be the number of, or not the number of ways, but the ways of performing the task. Like list them out and put them in a set. And since no two tasks can be completed at the same time, when I do this for each T sub I, right, now I'll have my A sub I's that correspond with each task. Since no two can be completed at the same time, that means that each pair of sets is disjoint. That there is no overlap between the sets of tasks. And so what that means is that this set of possible ways to perform the procedure, this collection, is it's pairwise disjoint. And so what the addition principle is saying is that if we do have this pairwise disjoint collection of sets, then each element of their union is a way to perform the procedure. And so that means that if we're counting the number of elements in this union, which we would want to do, so if we take the cardinality of that, what we get is it should just be the sum of the cardinalities of each set. And remember, this is when there's no overlap. So in particular, if they are pairwise, if it's a pairwise disjoint collection of sets, the intersection between any two elements is empty. That's when this works. In the next section, we'll talk about the principle of inclusion-exclusion, and that tells us more about when to recognize when this happens and how to compensate for it and still be able to get the count. All right, let's see some examples. All right, in this example, we'll count, how about 10-bit strings that begin with 110 or 1001. So here's my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my 10-bit string, and we know it begins with 110. And so there's two options for each of the remaining. And so we can count the number of ways to pick 110. So there should be 7 left, so there's 2 to the 7 ways to do this task. And then in this one, this one starts with 1, 0, 0, 1. And how many ways are there to do this one? Well, there would be 2 to the 6th. And so we'd like to invoke the addition principle and say it's the sum of those two, but we need to first check, is there any way I'm going to get overlap between my sets of solutions? So if I do something like this, is there any way I can end up looking exactly the same as doing this first procedure? And so what we really have to ask ourselves here, is there any way for a 10-bit sequence, 10-bit string to begin with 110 and end in 1001? Answer should be no. And so in this case, there's no overlap. 2 to the 7th plus 2 to the 6th ways total. How about another example? How many 10-bit strings begin with 110 or end with 1001? All right, we set it up again. We would have 2 to the 7 ways to do the first one and 2 to the 6 ways of doing the second one. Maybe let me draw those out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this first one begins with 110, and this next one 1001. And what's different about the last one? Well, we'll get overlap between these two. So in this one, in this second task, if I pick the number 110 and then blanks 1, 2, 3, 1, 0, 0, 1. Right, so let's say I pick a number like this, where I can put a 0 or 1 in each one of those, then that will be accounted for in both of these. Right, this one begins with 110 and ends in 1001, so there's some overlap. So how many begin with 110 and end in 1001? Well, that's a separate problem, but we can use the multiplication principle to solve it, right? We want to count the number of ways, and just like we did in the last one, we removed the extra set of duplicates, one full set of duplicates we took out there. So let's do the same thing here. The duplicates are exactly these kinds of strings, and there are 2 to the 3 ways to make such a string. So that means there are 2 to the 3 duplicates we want to remove, 2 to the 7th plus 2 to the 6th minus 2 to the 3rds. So already we're talking about how to compensate for this overlap. We'll talk more about that in the next section. But that's it for the multiplication addition principle. This is sort of our basis for the rest of this chapter. Yep. All right. See you next time.